Welcome back to Using Greg. Now today we're going to be looking at this Giandel, I'm not sure how to pronounce it. It's a Pure Sine Wave power inverter, 1200W unit I got off eBay from their official store. So just looking at the inside, the manual and the receipt. The inverter itself comes out. Actually not as heavy as I thought it would be. So that's the unit. So on one end you've got the terminals, the positive and the negative terminal, the neutral, the earth, a fan, which apparently only comes on when it needs to, which is really good. Then just heatsink on that side. The other end you've got a USB port, a cable for the remote, a couple of LEDs, a power switch, 2 outlets, and then nothing on that side, and just your standard warning. Good thing about this one compared to some others I look at is that had the little lugs for mounting the inverter, and also in the box you've got this particular one anyway, it's got a couple of cables, decent heavy duty cables, and also the remote, so you can mount that onto a fascia panel somewhere, and that connector there, that little phone connector, plugs into just that right there. So what I'm going to be doing now is wiring it up and testing to see how pure this Pure Sine Wave is. So I've got a few different types of loads I'm going to be putting on, and we'll see how good a sine wave it gives across different types of load. Okay, so let's now start wiring it up. So we've taken the earth wire onto the battery charger for the van, so that's already a good earthing point. So just for the sake of this test, I'm just going to loop it around the earth terminal. It's not how we'd normally do it, and we put a decent lug on there, but for the purpose of this, that should be fine. Okay, so hold the power button for half a second, and that's the noise. So not particularly noisy, and as you can see, the fan's not running at the moment. So the next thing would be to plug a load in and see how it performs. Now just to explain how I'm setting this up, firstly, this is fairly dangerous, so this isn't something I'd recommend you doing at home. I've got a 3-pin plug. This is the active pin, the neutral and the earth. So I've screwed the clamp for the cable onto the tip of the multimeter of the crow probe. I don't unfortunately have a clip for this crow probe anymore, so I've secured that in there. The earth is going onto the earth pin. I'm going to set it to 10 times on the probe, just so that's only taking through 1/10 of the actual signal power, so as to not blow the input amplifier on the crow. It's a very old crow, by the way, but it still does the job. So now I've shown you that, I'm now going to tape that all up so there's no way that anyone can touch in there by mistake, and then we'll plug it into the inverter and see how we go. So turn. That's a bit better. Okay, so you can see it's not a perfect sine wave. Definitely looks like it's about 50 Hertz. As you can see, we don't quite have it exactly as a pure waveform, so I wouldn't say that's a pure sine wave. So obviously what it's doing in the electronics is it's running half the waveform, and then it's running using some other transistors to run the other half of the waveform, and they don't quite line up perfectly. So the next thing to do will be to put some load on it and see how it performs. So for that we're going to turn it off. Now what they recommend is to have the inverter running before you put the load on, so we're going to make sure that's all unplugged. So this is now the crow. I'm just making sure that I'm running the crow off the inverter as opposed to off the main supply, just so there's no chance of getting any earth loop. So let's have the crow plug into this one here. And the first thing we'll do is to just do something really simple, like a mobile phone charger. Off we go, so that's on now. Wait for our waveform to come through. Here we are. And let's now just see how this works. Beautiful. It's charging. Does it go to fast charging? It does. And no sign of any dramas on the crow. Not the expected, considering how much power it draws. Okay. One thing I did mean to do was to measure the standby current draw. So let's do that now. Right, take that out. And we're going to pop this into the 20 amp range, because that's probably what we're going to need, I'd say. Once you start winding it up, in fact we're probably going to need more than 20 amps in the end. 20 amps out of 12 volts is only 240 watts, so we're going to be going through that without too much difficulty. But let's just see how much it uses on standby. Okay, so we've disconnected all of the loads, so that it's completely just running on standby, and let's see how much current it draws without any load. So just over an amp. So it's a little bit more than I would have expected, although it is a fairly big inverter. Okay, so basically working about an amp of standby current. So you wouldn't want to have it running unnecessarily. Alright, the next test is going to be just putting a laptop on charge. Could draw around about 100 watts, I think, from memory, 9500 watts. This is 19 volts, 6.3 amps at full charge, so 20 by 6 is 120, yeah, so around about just over 100 watts. That will draw. So let's turn it on just to get a base load current draw. So you can see we're around about 3 amps. That's running the crow as well, by the way. Wait for our waveform to appear. And now let's plug the laptop in. And it might help if we actually plug that into the computer too. Okay, so it's gone up to 5 amps. Our waveform still looks pretty good. I feel like that should be more focused than that, to be honest. Oh, that's better. That's a bit better. You can actually see that little step over here a bit more now. Alright, so it's charging the laptop fine. 5.5 amps. Which is, so considering the crow is drawing about, take a second. So standby current's about an amp. With the crow plugged in, it's drawing another couple, so about 3 amps. And with the laptop, it's drawing another couple of 2.5 amps. So up to 5 amps now. That's all looking good. And our waveform still looks okay. Right, our next test is going to be a hairdryer. Now to start with, this hairdryer is rated to 1800 watts, so that's more than this is going to be able to supply, but we're not going to take it up the whole way. So to start with, we're just going to run it on the fan setting, and then we might just run it onto the low heat setting. Let's see what that does. Okay, so that's about 9 amps without our heater. And if you look at the waveform, you'll see that it doesn't change at all. So that's fine. Now this is going to be the next interesting test to see how it goes on low power. Okay, I didn't like that. So turn that off. So it obviously overloaded it, so that turned it off. So that's fine. So it must be more than 1200 watts on low power. That's interesting though that it did that when it was considering that it's supposed to have a surge power of 2400 watts. So, okay, we won't take that one any further. So let's unplug that. Obviously the protection's worked. Turn that back on. Beautiful, all looks good. Wait for our waveform to come back. Okay, I actually expected it was going to do a better job than that. Now the next one is going to be an interesting one, because this is an old heat gun. And this is rated to 1200 watts. So it'll be interesting to see whether it can output what it's supposed to be able to output, which is 1200 watts, or whether it spits a dummy. Now actually I think for this one, so 1200 watts, it's going to be drawing 100 amps, so I won't be plugging the meter. So I think we might take the multimeter out of the circuit now, because that's not going to be able to do the job. Okay, so let's fire up again. So we've taken the multimeter out now, and let's see whether it can I mean, we're assuming that this is actually drawing 1200 watts, which would be 5 amps. Let's see what happens. Okay. Okay, so it survived that. That's looking good. I'm impressed with that. Because you can see that power stayed on. The waveform still looks good. The screen's actually dimmed a bit, probably because the supply voltage has dropped, I guess. We'll turn that off. That's not this, that's my neighbour. And the fan hasn't even come on, so that's good. Not sure whether that doesn't feel a little warm. I guess it wouldn't from that short band load. That's promising. What I'd be interested to do now is to actually see what the supply voltage does when we put that load on it. So let's pop the meter across the 240 volt output and see if the voltage is dropping, because I reckon it must be if that screen's got dimmer. So this is another one of these do not try this at home kiddies experiments. So I'm being quite safe about how I do it, but I'm under no illusions as to the risks associated with this. So we're going to put the, not that it particularly matters for AC, but we're going to put the black onto the neutral wire and clamps it on nicely. The red's going to go onto the active, as well as the crow probe. The earth of the crow probe is still on the earth of the pin, so the 3-pin plug, and then we're going to wrap this back up with electrical tape, just so there's no chance things coming. If something does come disconnected, it's not going to bring power out, of course, or 240 volts out. What it's going to mean is that particular monitoring terminal is going to be no longer monitoring. So let's carefully plug our collection of cables back in. Right, this is one you want to make sure we get this right. You definitely do not want to have this on the current setting, which we've already turned that off. Okay, so we're on the AC setting. This is an auto ranging meter, but apparently the voltage slowly ramps up on this inverter. So let's just see if we can watch that happen. So we've got our 2 lines multimeter going across the active and the neutral, and the crow running off the inverter, and our heat gun, which will be firing up in a minute. Okay, so 150, 170, yep, so you can see it's creeping up. 246, okay, so that seemed to do what they claim it is. And there's our waveform coming through. Okay, and again, that's the neighbour making that noise. So let's now put the heat gun on and see what our voltage does. Well, that's not too bad actually. Okay, that's actually pretty good. So it does drop down a lot initially, which is what you'd expect because it'd be a regulated supply, but it recovers quite quickly. So let's try that again. Let's set that onto the minimum. See what the minimum is set to. So it drops down to 230, which is still within range. It's probably only sort of 5% off what it should be. When I fired it up last time, I thought it came down to about 160. Let's try that again. Yeah, and you actually hear the heat gun ramp up in its speed. And there comes the fan on the inverter. See how warm that's getting. Not warm at all, just feels like air at the moment, but I guess it detects that it's got some load on it. That's not the quietest thing, but I guess if you're only using low load things, it's not going to matter. But the main thing is that it's still holding a decent waveform, so even at full load presumably, which is 1200 watts, which is what it's rated to, it's still able to hold a decent waveform. That's good, I'm impressed. Right, we've got 2 experiments to go. This is a different heat gun. We used to use this one here a minute ago, which is a standard, basically just a normal element with a switch. This one's a pulse width modulated temperature controlled one. Now it's rated at 2000 watts, so we're not going to be running that at full power. The way this one runs is that it will pulse the power going into the heating element to approximate an approximate temperature control. So that means it's probably going to be putting 2000 watt pulses onto the inverter. Now this has supposedly got a 2400 watt surge power, so it should be able to do it, so long as we don't take this onto more than about half its duty cycle. So this particular heat gun has got sort of settings of 1, 2, 3, 4, 5, and when it's running at 5, it's just connected the whole time. So I reckon if we're getting up to 2 or 3, we should be running around about 1,000 watts, and it would be peaking to 2,000. So this should be able to run it up until about setting number 3. So let's turn it on. Clear that minimum. Okay, so let's start it off on the coldest setting, which I don't actually think runs the heating element at all. Maybe very slightly. Now we'll start. The other thing I'm interested in doing is seeing whether the fact that this pulses the power is going to affect the clarity of the output waveform. Okay, so now you just hear the load come out, so it's obviously started to load up the inverter now. Every time you put a bit more load in it, you hear the fan speed drop down as the battery voltage drops, and then the inverter detects it's got a load and starts to bring it back up. In fact, you can see the little light on the Crow blinking. That's the pulsing of the pulse width modulator inside the heat gun. So it's actually making it a bit difficult for the inverter because the load is constantly changing. I don't know how long it's going to actually be able to do this. Oh, there we go. We got up to 2 and then it overloaded. So we'll turn it back down. I'll turn it off. Okay. Alright, so it's probably reasonable. We obviously, with this heat gun here, got supposedly, if that actually does draw 1200 watts, 5 amps, 1200 watts of power, they got full load. This one here was a bit of an approximation, but it did manage to get, well, I got up to the setting number 2, which I thought would probably be a little bit less than 1,000 watts or 1200 watts, but who knows, maybe it's a bit more. But the point is that even though the load varied around, the inverter was able to detect that the load had changed. It brought the battery voltage back up, or the supply voltage back up, but critically it held a nice clean waveform the whole time, and that's the sort of thing you'd really want from a good inverter. You don't want that waveform to start getting dirty once you start putting load on it. So I'm not sure whether it's actually supplying the full 1200 watts, or whether it's perhaps a little bit optimistically rated. I think it may be, but we've got one more test to do. So next thing I'm going to be doing is trying to run the microwave. So the microwave is a 1200 watt oven, and it's got a 1200 watt inverter, so we'll see whether it's able to supply that. Okay, so we've got power going to it now. Good, actually looks, that waveform looks slightly cleaner. I think it does, that's interesting. Not quite sure why that is cleaner now, but anyway. Alright, so let's now just give the microwave a quick run for, we don't have anything in it, but let's just run it for like 5 seconds or something like that. Yeah, voltage is, that's interesting, okay. It wasn't able to go for the full length, okay. So what I thought is that I have assumed up to now that when it's turned off it's because the load on the output has been too high, but it's possible that it could be because the input voltage has dropped down too low. And in the manual it does talk about the different types of failure modes it can go into. So under voltage protection and overload protection, but it doesn't seem to indicate particularly clearly what symptoms you'd expect to see. So what we might do is just put this back on, and we've got the multimeter sitting on the battery now, so we're not monitoring the 240 volts anymore. We're just monitoring the battery voltage. So what we might do is to put the microwave back on and just see whether this drops down to below 10 volts, which is the threshold at which it should turn itself off. Okay, so it was dropping down, but not quite as much as I would have expected. Certainly it didn't get down to 10 volts, which was the threshold that it's supposed to turn off at. So wrapping up, what do I think of this inverter? Well, I think it's a pretty good value. I paid about $130 for it off eBay, and I was very impressed that the sine wave was pretty well about as clean as I expected. I might have liked it to have been a little bit purer without that little step in the middle of the waveform we described. But what was important is that it was able to hold that type of waveform the whole way through, no matter what sort of load we put on it. And that's really important, as we talked about, not getting a dirty waveform when the load starts to increase. So you can have confidence that no matter what sort of load you put on here, it's going to be getting a clean waveform. I'm not so sure whether it's actually supplying 1200 watts. I mean, it did run the 1200 watt heat gun without any trouble. Whether that's actually full 1200 watts, I'm not so sure. I guess, in fairness to Giandel, we have to say that the heat gun was rated at as a 1200 watt heat gun, so we have to assume that it is consuming 1200 watts of power, which is what the device is rated to. So whether it's exactly 1200 watts or maybe 1100 or 1050 or whatever, you know, not too sure, but it's certainly in the right sort of ballpark. The other good thing about it is that it's not particularly heavy, so it's not too hard to mount like we've mounted it here. And also the fan doesn't run the whole time. That was something I was a little bit concerned about when I was looking at some other possibilities before I got this one. Some seem to run the fan the whole time, so this one only puts the fan on when it's needed, so that's another reason to buy it. It seemed to be able to supply the power we needed. It seems to meet the specifications roughly that they've claimed. It's pretty affordable. $130 for a 1200 watt inverter, I think, is a pretty good price. And also it comes with, you know, as we mentioned, the decent cables, and it also comes with that remote, which in this case we've got it mounted sitting like that, which I think is a pretty neat way to activate it. So I think if you're in the market for an inverter, you could do a lot worse than getting one of these. I'd definitely recommend this Giandel 1200 watt Pure Sine Wave Inverter.